Hi everyone, welcome back to the Sagar Tech Gate. If you are new here, so I am Dr. V. Sagar Reddy. So in this series, we will explore a Verilog HDL. It is one of the most widely used hardware description language in digital design world. Today, we'll focus on one of the most important and key modeling style in Verilog, data flow modeling. If you have ever wondered how these digital circuits like a adder, subtractor, comparator, multiplexers can be described using a single equation directly in the program, in the code. So this is exactly what a data flow model does. So in this video, we will explore in detail about a data flow modeling style with some suitable example. Already I covered one video on various abstraction levels in Verilog. If you didn't see that, please visit that video before watching this. So data flow modeling style. Verilog lets you design a circuit by focusing on the flow of data between registers and how the design processes that data rather than creating individual gates. So in data flow modeling, that circuit are described in terms of flow of data instead of what are the gates are used, how they are connected. So a continuous assignment is the most basic statement in data flow modeling. To describe any combinational circuits, we'll use a continuous assignment statement in data flow modeling style. So the continuous assignment statement provides a way to model a combinational logic without specifying an interconnection of gate, specify the logical expressions that drives the net. So in data flow modeling, we'll use a continuous assignment and the logical expressions to describe combinational circuits. So by using these, we'll define some relationship between input and output. By using this continuous assignment statement and these logical expressions, will define some relationship between input and output. So if you think Boolean expressions are Boolean relationship between the signals, in Verilog, this is done exactly with this continuous statement, continuous assignment statement. For example, if you want to design a simple AND gate, now how to describe the AND gate in data flow modeling? By writing a simple continuous assignment statement, assign out equal to A and B. Here we doesn't matter how many gates are there, how they are interconnected, what is the internal structure of that circuits. Just we will concentrate how data is flows from input to output, how we are processing the data between a signal. Simply, if you see, so in data flow modeling style, that operator acts upon these operands and provide a relationship between inputs and outputs. That is the reason, this is exactly what we need for a combinational circuits. So that is the reason we call this is a flow of data among the different signals. Clear? Now all such assignments are concurrent in nature. All these continuous assignment statements are in parallel. The order of execution of these lines doesn't matter. So I'll discuss in detail about a continuous assignment statement later in this section. Now for anything changes in the right hand side, if A or B changes, immediately it evaluates this expression and assign to the out. So that is the reason we can call it a continuous assignment statement. So now coming to this continuous assignment statement, a continuous assignment statement is a basic statement in a data flow modeling used to drive a value onto a net that may be both vector and scalar. Now see, let us a simple example here. Now here, assign out equal to in1 and in2. What is this simple AND gate here? Whenever if in1 or in2 changes, then it is evaluated this expression and assigned to this out. So what should be this out? It declared as a void type. So now in this continuous assignment statement, use it to drive a value onto a net. It should be that output should be net type only. That may be vector or maybe scalar. It should be void type only, net type only. Right? Now see, they model combinational logics. So these continuous assignment statements are used in data flow to model a combinational circuits. So they model combinational logic by specifying the logical expression that drives the net without detailing the interconnection of gates. Clear? So now the assignment statement start with the keyword assign. For example, see, I'll give simple example here. Right now. See, if we write assign cout sum equal to you write a plus b plus c. What this statement indicate? It is a simple full adder. Cout sum equal to a plus b plus c. So here we didn't discuss internal structure of this. Clear? So we didn't discuss internal structure of this. How many gates are there? How they are connected? If you see in the full adder, okay. So we have, if you use a 2 off adder, each off adder contain XOR gate and gates. Anyway, so we are not discussing internal structure of this circuit. Just you will write a Boolean expression. So Cout comma sum is equal a plus b plus c. It's simple. We will use operators to write this Boolean expression. We are assigned to sum, okay, value to that net type. So here, without detailing the internal interconnection of the gates, how they are connected, how many gates are used to describe this hardware, doesn't matter in Dataflow modeling. Just we want to focus how data moves in the circuits, the flow of data. Okay, right. So this assignment expression is evaluated whenever the value of right hand side changes, will update the output signal. For example, if anything changes in the right hand side, it will evaluate immediately and assign to this output signal. So we'll update it as output signal. So if anything changes in 1 or in 2, if any value changes in the right hand side, then it will evaluate that expression and assign to this out. So that is the reason we call as a data flow of data between over the networks, wide network. So the LH of a continuous assignment should be Y type only. It should be Y type. That is a thumb rule you need to remember. So if you use a continuous assignment statement, that LHS should be Y type only, net type only. Now see, the operands on the right hand side can be registers or net or function calls. Already we discussed the data types used in Verilog. So if not, please visit that video. So you'll get a clarity. What are the different data types are there in hardware connection point of view? What is meant by reg? What is meant by wire? So when should I use these reg and wire? Then we'll get an idea. So now the right hand side operand may be a reg type, maybe a net type, or maybe a function call also. Right? So now see the simple example, wire a comma b comma c. So assign c is equal a and b. This is a simple AND gate. Clear? Having two inputs a and b. Clear? The LHS of continuous assignment should be Y type only. It should be, this C should be Y type only. You remember that point. Right? Now see, we have a different type of assignment statement in Dataflow modeling. One is implicit continuous assignment. So now see here, wire out, assign out equal to in 1 and in 2. So what is this? This is a regular continuous assignment statement. This is a regular continuous assignment statement. So here, if you want to write in implicit way, so wire out equal to in 1 and in 2. This is an implicit continuous assignment statement. So what is the difference between here? So we didn't use a keyword assign. Directly by using wire out equal to in 1 and in 2. Like that also we can write. Clear? So now assign C is equal A and B. So this is a continuous assignment for net type. C is a net type. So now assigned data 15 down to 0, data 15 down to 0, XR data 15 down 0. This is a continuous assignment for vector net. It should be net type only. Yes or no? So here this is a net, this is a vector net. It should be a scalar or it should be a vector. Clear? Now assign C out sum 3 down to 0. This A 3 down to 0 plus B 3 down to 0 plus C in. So concatenation of scalar, net and vector is also possible. We can concatenate both scalar and vector type, net type only. So what do you understand from this? So we are using these continuous assignments to model a combinational circuits in Dataflow. So it contains, continuous assignment means that it contains simple Boolean expression. So by using this continuous assignment and Boolean expression, we'll describe the combinational circuits. Now delays. So it's very important concept. So actually the delays are not synthesizable in Verilog. So we cannot synthesize delays, but to mimic actual gate behavior, Gate has some propagation delay. To mimic that behavior, we will introduce these delays. We have different type of delays we'll discuss. So delay values control the time between a change in the right hand side operand in the continuous assignment and when the new value is assigned to the left hand side. Now see, I'll show one example. So how many types of delay statements are there? Basically, we have three ways we can specify delays in the continuous assignments. So delays are not synthesizable. To mimic actual gate behavior, okay, we are using these delays. So these are the three different delays: a regular assignment delay, implicit continuous assignment delay, and net declaration delay. So these are the three different type of delays we are using, okay, to specify the delays in the assignment statement. So first one, regular assignment delays. So the delay value is specified after the keyword assign. Now here this is a simple example. Assign yash 10 out equal to A and B. What is that? Here delay in a continuous assignment. So the delays are specified in Verilog by using yash. So yash 10. So 10 time units delay we are providing. What is the meaning here? So now it evaluated A and B. If anything changes in the right hand side, it evaluated, assigned to the out after 10 time units. Clear? So any value change in the A or B will result in a delay of 10 time units before recomputation of the expression A and B, and the result will be assigned to out. What is the meaning of before recomputation? For example, if I specify yash 10, then it hold 10 time units, then it evaluate A and B, then assign to this out. Before recomputation of the expression, nothing but it won't compute that expression, it won't evaluate, it wait 10 time units, then it evaluate that expression and assign to the 10. So we'll show one example. Now in this here, so we have A and B. Let us consider for this example. So what is the delay here? 10 time units. So out is equal to A and B. So now this A and B. Now this is the out. So now at time unit 10, if we see at time unit 10, what is that? Both A and B are 0. Both are 0. In case of AND gate, what is the output? Out also 0. Now here 0. Till this time unit 30. If you see here, both A and B changes. A become 1 and B becomes 1. Both are 1. So in case of here at the time unit 30, both are 1. Now A and B is 1. But what is the output? Output updated at time unit 40 only. So out equal to 1. So after 10 time units delay. Clear? So A and B changes. Then it updated, it evaluated that A and B and assigned to this out after 10 time units. At the time unit 40, then out equal to 1. So even though the AB changes at 30, then the updation at 40 only because the delay is 10. Now see here, now A changes at time unit 60. What is the B value? B is same. But after 10 time units delay, clear, it evaluated. So A is 0 and B is 1. Then we are assigned to this out as a 0 after 10 time units delay. Now see here, what is that? So now here A changes from 0 to 1 at time unit 80 and it becomes 1 to 0 after 5 units of time. Then you may expect as it is this pulse width may appear at the output, but we won't get. So this a pulse width less than specified assignment delay. What is the delay here specified? 10 time units. So this pulse width is 85 minus 80, only 5 time units. This pulse width is less than this actual delay. Clear? A pulse width is less than specified assignment delay is not propagated to the output. So this delay is called inertial delay. I'll tell you. So this pulse width between 80 and 85 gets filtered out. It won't propagate to the output. Because now what you understand from this? At least the input should be stable at least this 10 time units. In this statement, A and B should be stable, okay, at least 10 time units, then only it will propagate. Even though if you change A and B, it should be stable for 10 time units. For example, if this A changes, okay, from 0 to 1 at 80 and 1 to 0 at 85, what is the duration here? Only 5 time units. But, so actual delay is specified 10. So it is less than this 10, so it won't propagate to the output, okay. It won't. It get filtered out. I'll explain in detail if you want, right? So this is the inertial delay. Now say simple example, assign hash4 out equal to a. This is a simple buffer out equal to a. Whenever a changes, then after 4 time units, then assign to the out. Now see in this example, now a at 5, now it become 1, 0 to 1. Now a become 1 until 8. So how many time units? 3 time units. 8 minus 5, 3 time units. What is the delay specified here? 4. Nothing but, so we won't get this 1 as an output in this case. Now what should, after 5, after 4 time units, 5 plus 4 at the 9, we should get 1 actually. Yes or no? So now if it is 5, now the delay is the 4 time units. 5 plus 4 at the time unit 9, we should get a 1 because a equal to 1. But we won't get. We didn't get this. Out equal still 0 only. Why? Because the a is stable only for duration of 3 time units. It is less than 4. If the a is stable at least 4 time units, then only it will propagate. Now see here, what is that? So now here at 13, then input changes from 0 to 1. Now it is stable till 18. So how many time units? 5 time units. 5 time units. So 18 minus 13, 5 time units is greater than 4. Now it will be propagate to the output. So now here 13. So 13 plus 4, delay is the 4. 13 plus 4, 17. Then at 17th time unit, the output gets, okay, the output changed as a 1 from 0 to 1 because a is changed from 0 to 1 at 13. So the delay added plus 4 at the 17, the output changes as a 1. Now see in this case, now here input is changed from 1 to 0 at 18 and again that input is changed from 0 to 1 at 20. Now what is the duration here? Only 2 time units duration. What is the delay here? 4. So now we won't get this pulse. We won't get this pulse. It is filtered out. The output is remained same. Clear? Right? Now here input changes 1 to 0 at 26. We are added a 4 time unit delay at 30. Then output is 1 to 0. I hope you understand. Now what do you understand from this? A value change on the right hand side. This a right hand side must hold steady state for at least the delay period before it can propagate to the left hand side. So that whatever the value change in the right hand side should be stable, hold steady state for at least this delay period. Then only it can propagate. Clear? To the left hand side. If the value on the right hand side changes within the delay period, for example here the changes only 2 time units, it again back to 1. Yes or no? So now the delay here, the duration is less than this time delay. If the values on the right hand side changes within the delay period, the former value does not propagate to the output. Now here this pulse didn't propagate to the output. It get filtered out. Here also this pulse get filtered out because the duration is less than this delay. I hope you understand. Now assign a to out only if the inputs have been stable for the delay duration. Clear? So that a to out will get out is updated only when a should be stable at least this delayed. Clear? I hope you understand this inertial delay. So why we need delay? So these delays are not synthesizable, but why we need this delay concept? To mimic actual gate behavior. Actually in the real time the gate won't immediately respond. It has some propagation delay. Clear? In that propagation delay, if anything changes input, it won't get updated. Clear? Right. To mimic actual gate behavior, we are using this delay concept. But in the simulation, okay, these delays are not synthesizable. Clear? So implicit continuous assignment delay. So this is another type. So we know that wire #10 out A and B. So this is implicit continuous assignment delay. Just we didn't use just assigned keyword. Directly we write wire into that statement. Clear? So it is equal to wire out assign #10 out equal to A and B. Both are same only. We can write like this also. Clear? Net declaration delays. So this is another example. So wire #10 out. We can write assign out equal to A and B. So you can specify the delays here also. So in this statement, we are specifying in the assign statement where Net delays means we are specifying the delays while declaring this out as a net type. While declaring itself, in the declaration itself, we are specifying the delays. Here, we are specifying the delays in the continuous assignment statements. So there is a difference. These are the three different delays used in the continuous assignment, okay, especially in the data flow modeling style. So now this we can write assign as10 out equal to A and B. Both are same only, right? Right. So example for half adder. So now here I'll explain few example how to design, how to model these circuits using the data flow modeling style. Now here, so this is a simple half adder having a two inputs A and B, sum and carry. So now in data flow modeling, what we use continuous assignment statement, a simple Boolean expression, yes or no? So we are not worried about how many gates are there, how they are interconnected. Clear? So just we want a Boolean expression, we want a relationship, Boolean relationship between input and outputs. Just will concentrate how data flows from input to output, how the data will be processed. Clear? Understood? So here simple half adder. What is the truth table for half adder if you see? Having A and B, sum and carry. So 0, 0, 0, carry 0, like that you will get. This is a simple truth table of half adder. If any input is 1, then output is 1. If input is 1, output is 1. Here both are 1, then sum is 0, carry is 1. Clear? This simple truth table of a half adder. If you observe this truth table, what is the sum? So directly no need a K-map here to simplify this simple truth table. So this is XOR. What is this? If you observe this carry, this column, this AND gate. So you know the relation. What is the relation between the A and B, A comma B and sum? Just simple XOR relationship. What is the relation between A, B and carry? This is AND relationship. Now see, sum is equal to A XOR B. So XOR gate. So carry is equal to A and B AND gates. How do I write in these? How do I implement these gates? Using simple operators. Now see, in data flow modeling, so anyway, we write assign sum is equal to A XOR B. Simple, very simple. Directly we can write. Okay. So assign carry is equal to A and B. Directly we write a Boolean expression in the code. Clear? So here module, anyway, module name, half adder. These are the ports, input A, B, C, sum, carry. These are the declaration of input ports A comma B, sum and carry. So assign sum is equal to A XOR B. Assign carry is equal to A and B and model. You may think, sir, you mentioned that LSS should be a wire type. Clear? In the continuous assignment statement, that LSS should be a net type, a wire type. So default, all signals are wire type only. So until you mentioned as a reg, okay, it is a default wire type only. This A, B, sum, carry, all are wire type only. No need to declare. Clear? So now by simple two statements, we can design this half adder. Simple Boolean expression. This operator acts upon these operands, produce like a relationship between the inputs and outputs. That is the reason we call it is a flow of data. Okay, data flow modeling. Clear? Now another example of full adder. So having three input, clear, sum and carry out. This is a simple truth table. Okay, here my intention is to just how to write, okay, code like in data flow model, how to model a simple circuits in data flow modeling. Clear? I am not intention how we are solving these, how to find the K-map. It doesn't matter here. Just for understanding, I am giving these examples, right? Now see, this what is that sum? If you use K-map, this sum is equal to A XOR B XOR C. Clear? So this is a carry expression, AB plus B, Cn plus ACn. Even though if you write directly, we will get. So this is the BCn. Here 1 is there, A into Cn. Here 1 is there, A into B. Here 1 is there. Okay, simply you can write it. Clear? My intention is not to find the K-map for sum and carry. Clear? Just if you want, you can pause the video and try to find the sum and carry expression by using this K-map. Clear? So I get some Boolean expression. I need some Boolean expressions. Clear? So how do I write this full adder code in data flow modeling? Right? Module, full adder. Clear? These are the inputs. Input A, B, C, N. These are the ports we can declare as an input A, B, C, N, and sum carry as output. Simply I can write assign sum is equal to A XOR B XOR C N. Assign carry is equal to A and B or B and C N or A and C N. This is a simple Boolean expression I'm writing directly in the code. Clear? I hope you understand. If you know that Boolean expression, if you know the relation between the input and output, directly we can write this one. Even you can write adder also. Directly you can write sum is equal to a plus b plus c. Directly we can write by using that operator. Clear? I hope you understood. So how to write directly? We write a sum expression and carry expression using continuous assignments. So what is the meaning here? For example, if A or B or C, anything changes in the right hand side, immediately it evaluated that expression assigned to this sum. Clear? If any of the operand, any of the signal on the right hand side changed, immediately it evaluated that expression and assigned to this LHS side. That is a continuous assignment statement. It is not a simple assignment statement. Continuous assigned statement. Nothing but if anything changes in the right hand side, immediately it evaluates that expression and that final value updated as a LHS. Clear? So now this is simple mux. You know that, okay? 2:1 mux based on the selection line. So that y may be equal to I0 or I1. See the truth table. If selection line is 0, then y is equal to I0. If selection line is 1, then y is equal to I1. Clear? So how do I write? Just pause the video, think how do I write. So we already discussed the various operators in Verilog. If you didn't see that video, please watch that. In detail, I explained various operators used in the Verilog. If you're good at operators, directly if you know relationship, directly you can write the Boolean expression for output in terms of input in the data flow modeling styles. Just we'll use the Boolean expressions. It contains some operators and operands. If you know how effectively I can use these operators, okay, right? Now see, y is equal s bar I0 plus s into I1. This is a simple Boolean expression. So what I write in the data flow modeling? So module name. These are the ports, inputs and outputs. So I0, I1, s as input here. I declared as both are input. Then y as output. Then assign y is equal. These are conditional operators. So why only conditional? You can write a simple Boolean expression also. You can write this also. This expression as it is, you can write it here. Clear? So complement s and I0 plus or s into I1. Like that also you can write it. Just I'll use a conditional operator. So now y is equal s question mark I1 colon I0. If s is true, if it is true, then we'll assign this true expression to the y. So now y is equal to I1. If s is false, then y is equal to I0. Like that, this is a very simple way we can model a combinational circuits in data flow modeling, right? So, and another example is mux, 1:2 mux. So, one input and two output based on the selection line, whether that I0, okay. So, I may be forward to y0 or maybe y1. Now, see this is a truth table. If selection line is 0, then y0 is equal to I. If selection line is 1, then y1 is equal to I. Either maybe 0 or 1, then it connected to the y1. So now these are simple Boolean expressions. Y0 equal to I and selection bar. So S bar, selection bar, okay, into I. Clear? S bar into I. We'll get understood. It's a very simple logic. If selection bar is 0, 0 prime 1, I into 1, we'll get y0 is equal to I. So selection line is 0 means 0 into something, y1 equal to 0. If selection line is 1, okay, 1 bar, 0. So that whole expression is 0, y0 equal to 0. So if selection line is 1, so y1 is equal to I into 1, then y1 is equal to I. This is a simple Boolean expression for a given 1:2 demux. Now this is a simple code, module name. So we can declare inputs, okay, input wire I1, input wire selection, output wire y0, y1. Sir, till now you declare those ports as a input and output after this. Clear? You can write like this also. You can declare inside this parenthesis also. This is a good practice actually. Clear? You can declare this I as a input, that to wire type. You can directly declare data type as well as the whether it is input or output. Direction also you can specify. So now selection line as input, input wire selection line. Output wire y0 comma y1. So what is that actual equation? Okay, continuous assignment statement. Assign y0 is equal complement selection, negation selection, selection bar. Clear? Selection bar into this and symbol into I here. So assign y1 is equal selection into I1. Directly we can write this equation, Boolean expression as a continuous assignment statements. We use the keyword assign. Assign y naught equal to complement selection line and I1 for this y naught expression. For y1 expression, assign y1 is equal selection and I. This is a simple way to write, okay, model the digital circuits using Dataflow model. See another example. So 4:1 multiplexers. So now having how many inputs here? 4 inputs. Here 2 selection lines. Clear? So I0, I1, I2, I3 and S1, S0. This is out. Clear? So now what is the truth table? If both are zeros, S1, S0 both are zeros, out is equal to I0. If 0, 1, out equal to I1. 1, 0, out equal to I2. 1, 1, out equal to I3. Based on the selection line, that output may connected to I0 or I1 or I2 or I3. Clear? So we don't want how these circuits are implemented, how many gates are used, how they are interconnected. Okay, it doesn't matter for us. If we know the relationship between these signals, then you can write that expression. So now what is the expression now? See, S1 bar S0 bar into I0 equal to this y. Yes or no? So now simply we can write. So model name, inputs wires I0, I1, I2, I3 and input wire the selection line S0 and S1 and then output wire, so out. So how do I write this? Assign y is equal to, now see this expression, this negation S1, negation S0, complement S1, complement S0. So complement S1, complement S0 into I0. If for example, if both S0 and S1 are 0, 0, then 0 complement 1, 0 complement 1. So 1 into 1, 1 into I0, then y is equal to I0. Remaining all cases, we'll get 0, here 0, here 0. So y is equal directly I0 when S0 equal to 0 and S1 equal to 0. Like that you can write. So here S1 complement and S0. S1 complement and S0 into I1. For example, S1 is a 0. So 0 complement here. Negation of S1. 0 complement means 1. These are not gate. Simply we can write. Okay. So like that not gate. Okay. So this complement. So 0 means 1. Complement of 0, 1 and S0 is 1. 1 into 1 and I1. So then y is equal to I1 when S1 is 0 and S0 is 1. So remaining all these cases will get a 0 only. Clear? Directly you can write the Boolean expression by using these continuous assignment statements. I hope you understand, right? So here my intention is Dataflow modeling is very easy if you are good at operators. If you are able to write a Boolean relationship between input and output, then it's very easy. These continuous assignment statements are used to model only combinational circuits, right? I hope you understand this Dataflow modeling style. I discussed some examples also. Thank you very much.